So welcome to the survivors. We still have 2 lectures, and they are the smoothest lecture, at least in my part. So if you made it through here, then you will make it through the last remaining 2 lectures. So where are we? So today we'll study percolation on half-planar infinite maps. And so the first theorem I want to prove is the following. I fix an admissible weight sequence Q so that I can define, this measure P infinity on half-planar maps, infinite planar maps of the half-plane. And then what I will do is do phase percolation conditionally on this map. So I first sample the map M, and then I color each face of the map either black, this is black, or white, this is white, with probability respectively P and 1 minus P independently of each others. And then I ask if I have an infinite black cluster or not. And it turns out that there is some function, we'll see very simple function of Q that we can compute for any examples that you may come up with. A parameter, PC, a critical threshold, so that if P is less than PC, then we have no infinite cluster in the map, almost surely for the map and for the percolation. Whereas if P is larger than PC, then you have a unique infinite cluster. When I speak of cluster, I implicitly think of black cluster. Right? So this is the picture here. And we'll come back to this after, but I promised that I will give you a very nice proof, at least one nice proof during this lecture. So it's not a proof due to me, of course, otherwise it could be nice. It's a proof due to Neveu of the strong ratio limit theorem. So don't forget to sign the attendance sheet. So what was the theorem? So it's really something that I promised yesterday. And I hope that you guys have tried hard to solve this problem. Otherwise, you won't appreciate the simplicity of the proof. So what is the setup? You let yn be a random walk, let's say mu random walk on Z, with mu aperiodic step distribution. Okay? Started from 0 implicitly, and we assume that y is recurrent. And if so, then we have the so-called strong ratio limit theorem, the limit as n goes to infinity of the ratio of the probability to be at time n plus n0 to be at some particular value L0 divided by the probability for yn to be at 0 at time n. This for any n0 and L0 fixed. This ratio goes to 1 as n goes to infinity. Okay, that's the strong ratio limit theorem, which in this form is due to Spitzer and Kesten in the late 60s with a very long proof. Okay, who tried to make a proof of this theorem? Yes, thanks, Paul. Well, kind of. It's up to you. You will see the proof is really simple, but you won't appreciate it. Let's do it anyway. So proof. Okay, so clearly, if I can prove to you that for n0 is equal to 1 or minus 1, and for L0 to be in the support of nu, so if I prove that the ratio of yn minus 1 to be at some particular guy b divided by yn to be at 0, if I can prove this for any b in the support of mu, since mu is aperiodic, if I can prove that, then it's very easy to prove this by aperiodicity, right? all right? So I will prove this. And the key idea to prove this is to introduce the following variable. Let's say big N, little n is the number of i's less than n, such that the increment yi minus yi plus 1 minus yi is equal to b. That's the number of steps of size b in my random walk. Okay, so now let's see what is this. What is expectation of nn divided by n conditionally on yn to be at 0? Okay, so let's see. This, by cyclic exchangeability of my increments, is just the probability that y1 is equal to b, knowing that yn is equal to 0. Why? Because, you know, each increment here is the increments of my walk are cyclically exchangeable, so they play the same role. And here I've got n increments that could be equal to minus b, to b, sorry. Since I'm dividing by n, this is just plain, right? Okay, so this is just by cyclic exchangeability of the increments. Okay, but why is this? Well, this, you apply Markov. So if you make a step of b, sorry, let's put it minus b here. If you does a step of b, and if I want to be back at 0 at time n, this is just equal to, okay, so the probability that y1 is equal to b and yn is equal to 0 divided by yn is equal to 0. And by Markov, this is just mu, I want the first step, sorry, mu of b, I want the first step to be b, and then I want that started from b, I'm back at 0 at time n, so that's just probability that yn minus 1 is equal to minus b. So exactly what I want here, all right? So far, just trivialities. So this is exactly the ratio I want to prove is converging to 0. That's the ratio I wanted to 1, sorry. So what I want to prove is that actually this quantity here is very close to mu of b. All right? So let's see what this quantity is doing. So what can you tell about this big guy, n of n, without the conditioning? So what is the law of n, big N of n, without the conditioning? Well, I have a mu random walk, and each of my increment has a probability mu of b to be equal to b. So this guy, under the random walk, under the mu random walk, is simply a binomial of parameter mu of b launched n times. Okay? So let's see what this guy is doing. So if I had no conditioning, this binomial should be very concentrated around its mean value. And so if I divide by n, this should be very concentrated around mu of b. But you may say, yeah, but I have this conditioning. But now the key is that this guy is really, really, really strongly concentrated around mu of b. So let's see that. So let's write expectation of n little n divided by n, knowing yn is equal to 0, minus mu of b. So let's see what it is equal to. So you may say, oh, okay, either this guy is close to mu of b, plus or minus epsilon, or this guy is far from mu of b, plus or minus epsilon. So this is less than, say, epsilon, plus the probability. If it's far from mu of b by an epsilon, you just bound this quantity by 1. So you just have the probability that minus mu of b is bigger than some epsilon, knowing yn is equal to 0. And now this guy, you just upper bound plainly by the probability that just this guy without the conditioning is larger than epsilon, divided by the probability that yn is equal to 0. Okay, and now you're here, you say, I will actually prove a stronger theorem. I will prove that, I will not assume that yn is recurrent, but I will assume that the probability that yn is equal to 0 decrease sub-exponentially, meaning as n goes to infinity. We will see that this actually implies this. But let's suppose this. So if you suppose this, for any epsilon positive fixed, the quantity on the top, by an easy large deviation argument, is decaying exponentially fast in n. Whereas the quantity below here does not decay exponentially fast. So this ratio clearly goes to 0. And so you're left with just an epsilon here. So if you plug this back in this equation, you clearly see that this guy must go to 1 as n goes to infinity. Okay? So it's a bit sketchy, but I wanted it to fit on a single board. That was my promise. So this is a half board calculation, but clearly it's a gem because if you look in Spitzer and Kesten, this was really 35 pages calculation, really, over 2 papers. So now let's see why if yn is recurrent, I have the probability to be back at 0, that this probability does not decay exponentially fast. Why is that the case? Well, you need, okay. Clearly, if this decays like, I don't know, half to the n, then you know that you're transient, like, right? Because you can sum this probability. But here, I really need that this guy is converging. But actually, this guy is always converging. This guy here is always converging. Do you see why? Yes, subadditivity. So the probability to be back at n plus m at 0, this is at least, so super additivity, this is at least the probability to be back at 0 times the probability to be back at 0 at time n times back at 0 at time m. Okay? And so this, by standard super additivity argument, implies that actually this probability is converging. The 1 over n. This is converging towards some constant c belonging in 0, 1. Okay? And now that's clear that if you're recurrent, this constant cannot be strictly less than 1. Because if it were strictly less than 1, then the sum of the return probability at 0 would be finite. And so you would be transient. Okay? So actually, as usual, if you want to prove a theorem, you need to find the right assumption, which might be lead to a stronger theorem, but for which the proof is easier. Okay? Questions about that? So this argument is due to Neveu, and really the key is to write this via cyclic exchangeability as concentration of a binomial random variable, and whatever the conditioning, if this conditioning is not too nasty, meaning you're conditioning on an event of not exponentially small probability, then this guy is clearly concentrated around its mean. All right? May I raise? Okay, so that's called the strong ratio limit theorem. And hope you will remember that each time you will see a ratio like that, because it's really useful. All right. So let's come back to our percolation problem. So yesterday, we already kind of see how to explore a percolation cluster to know whether it's finite or not. But let me put that in a rigorous, on a rigorous ground. So for simplicity, so you remember yesterday we said that's my half plane. I will not color the face on the right-hand side of the root edge. I will color it in white. And I will color all the other faces either black or white with probability p in black and 1 minus p in white. What I will actually be doing, just for convenience, is I will assume that my root edge, I split it. So I split my root edge into a two-gone, and that I will deterministically color the two-gone that I have here in blue, in green, so in black. Okay? So this will be my starting configuration, which is the case here. Okay? So let me describe for you now the peeling algorithm. So the algorithm is this one. So we'll do a filled-in peeling, as usual. So assume that En, the part that you have explored up to time n, has the following form. So we will assume that it has, that's the part you've got explored. Your root edge was here. You had some black guy here. That's hard for me, the black guy. And we will assume that you have a part of the boundary here, so that the faces adjacent on the right of this part of the boundary, they are black faces. And all these black faces, they are connected. They are part of the cluster of the root edge. Okay? That you have something like that. So you have a few faces here. And for all these faces, the faces on the right here, they are black and they are connected to the origin cluster. And not this one. This one, they are white. I'm confusing the color, sorry. Okay? So we'll assume that we have this boundary condition. So in the rest of the talk, I will denote this boundary condition like that. This is black, and the rest is white. Okay? That's my boundary condition. So if I'm facing such a boundary condition, I have to tell you which edge I want to peel. And remember what we did yesterday. We said, we want to go from left to right in the castle and try to follow the cluster. So if we are going from left to right, we will open the door which is leftmost among all the doors that are connected to a black room. So we will open that door. We want to peel that edge, this one. So that is A of En. Okay, that's my algorithm. But of course, if you want to use this algorithm, you have to check that this boundary condition is preserved under applying my algorithm. So let's see what can happen. So I have my black boundary condition here, and I'm peeling this edge. So what could happen? So the first thing that could happen is I discover a new face. And then you have to choose whether this new face is black or white. I mean, the map will tell you if it's black or white, but you have the two options. So if it is white, like here, I claim that the boundary condition is preserved, because if you go along the boundary here, you see that the faces adjacent on the right, they are all white. That's a vertex, this guy, so it's not an edge. the next edge is this one, so white, 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 white. Then I have black, and then white. So my boundary condition is again of this form. Okay? You may say, ah, no, but I have this vertex touching the black. Yes, but that's a vertex, that's not an edge. Here, all the faces, they were like that, and I had no faces here which were black. Okay? The other option is that the face I discover is actually black. And here again, if I follow the boundary and look at the color of the faces on my right, what do I see? White, 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 and then black, 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 and then white. So again, it's of this type. Right? So that's for the CK events. Otherwise, I have my gulp event, so meaning that this edge will be identified with an edge on the boundary, either on the left or on the right. So let's see on the left first. If I have something that I glue on the left, this is the picture that I see. So that's the edge I want to peel. And that's my boundary condition. So this was black, 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 black. And then the rest is white. And here, with my color rule, this is yellow. That's yellow, not black. Huh? So let's see if the boundary condition is preserved. What do I see when I go along the hole? I see white, 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 black, 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 white, 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 white. OK, that's correct. And the last case is if I glue this edge with one adjacent on the right-hand side. So what do I see? I see something like that. So that's the edge I was peeling. That's my boundary condition. Black, 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 black. And that's the hole I was swallowing. This stops here. So what do I see in my hole here? So again, the color code is this is blue, this is blue, this is blue, 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 and blue. So what do I see on the blue thing? White, 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 black, 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 white, 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 white. OK, that's again of this type. So let me make a last drawing, which may tell you that actually, after a step of that sort, we may stop the exploration. And that could happen if actually, when I'm swallowing a part on my right, so when I'm swallowing something like that, actually the whole boundary, whole black boundary was swallowed in this peeling step, meaning that I'm identifying an edge here with an edge there. If I do so, I glue, and this whole black part becomes interior of my explored map. And so what do I see as a boundary condition now? I see white, 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 white. Only white. And so if this happens, blue and yellow, if this happens, then I say we can stop the exploration.
This can also happen by discovering an empty.
Yes. Yes. The stop, we will make it clear after. The stop is when I don't have any black region on the boundary of the hole anymore. Is the algorithm clear? So far we were not speaking about probability. That's just deterministic statement. That's the algorithm I use to peel my map. So proposition, very easy. The proposition is saying that the cluster of the root edge, so if C is the cluster of the origin, so the cluster of the guy I started with, then the proposition is just this cluster is infinite if and only if the A, let's call it this A-Perco for the A-Perco algorithm, the A-Perco exploration goes on forever. Okay? if this algorithm goes on forever, there is a slight point here. If I keep, okay, no. Actually, I think it's a, do I need probability or not? I think not. I think not. Yes, that's correct. Okay, so if this goes on forever, you clearly see that you need to discover an infinite number of new black faces because of Rémi's remark that we are always swallowing one edge on the black part at each step, at least one. So at some point, we will need to create some new black boundary. On the other hand, if this algorithm stops, that means that we are in a step like that or a step like that with a boundary 1 at some point. And so we see that everything we discovered so far is enclosed in the map that, that is here, and that the cluster cannot grow further than this. Okay? So that's deterministic, and I'm not proving it. Draw a few pictures, and you will be convinced of that. Okay? So now comes probability. So if we do probability now, what we will need to keep track of is this process, Bn. What is Bn? Bn is the length of the black boundary during the exploration, the E-Perco exploration. So clearly, that's E0 here. What do I have as a starting configuration? My length of the black boundary at the initial step is just one black edge. Okay, I have just one black edge. Okay, so to relax a little bit, let's proceed with this algorithm on this example. Okay? So what do I see? So I start with this guy here, this black face, which is my only boundary, my only black boundary. And then according to this algorithm, I want to peel this edge here. So this is the same in the map as discovering this edge here. So what do I see? So I'm facing an event like that, where I discover a new face, which turns out to be a quadrangle, and which is a black face. Okay? Then this algorithm tells me, oh, peel the leftmost black edge, which is this one. So I'm here, and I'm discovering this edge. So what do I see here? That's an event of type G0 infinity, meaning that actually I'm gluing this with this, and my new boundary is like that. Agreed? Okay, so my new boundary is this one, and I'm peeling the leftmost black edge along this boundary, which is this one. So I'm discovering this. What do I see? I see a new face of degree 4, which turns out to be white, like this. Okay, so then I look along my boundary, and I peel the leftmost black edges, which is this one. And so I'm discovering this edge in the map. What do I see? Let me make some room here. What do I see? I discover a new room, which is an hexagon. 1, 2, 3, 4. Up. Is that an hexagon? Yes. And this hexagon is black. Good for me. Well, if I want to go on with black. Okay, then I peel this one. What do I see? Ah, I see that this edge takes me back to this face. That means that I add a G0 infinity event, and that actually this edge is glued with this one. All right? Then I peel this one. We're almost there. If I peel this one, what do I see? I see a new face, which is a quadrangle white. Then I peel this one, and I see a two-gone black. Then I peel the leftmost black edge, which is this one. And what do I see? I see that this takes me to that room. That means that actually this edge and this one, they're glued. All right? Then I peel this one, which is this one, and it takes me to the outer face. And so what does that mean? That means that actually I'm making an event like this one, and that this boundary does something like this and comes back here. Okay? Agreed? And this part, I don't care. I have not explored this part, but I can tell you for sure, without having explored that part, I can tell you for sure that the cluster of the origin is finite, because it cannot extend further than this, and maybe in this part, but it's a finite part. Okay? Convinced by the algorithm? So if you're convinced by this algorithm, let me introduce two quantities that will be key in the following. So during a peeling step, which is either something like that, or something like this, or something like that, that's during a peeling step, I will introduce three quantities, which is GL, E, and GR. This is the left gulp. This is the exposed boundary, and this is the right gulp. And what is it? This is the number of edges swallowed on the left, strictly, of the peeling edge. In this quantity, that's 0. Here, that's 0. And here, that's this number here, this number of edges here. That's GL. Similarly, this is GR. And the number of exposed edges, I have to tell you what it is. Exposed, well, let me tell you on the picture. That's the number of edges that you expose during a peeling step of type C. Okay? So once I have those random variables, what do you think about this process Bn under this algorithm? So what do you think it evolves like? Even better, it is a Markov chain indeed, but it's even better than that. But I just want to see if somebody is actually, there is a dead body under the carpet here. But it was a small animal. But there is something dead under the carpet. Don't you smell? The thing is, so far, the peeling algorithm that we were using, they were deterministic functions of the map. Is this one a deterministic function of the map? No. No, because it's a deterministic function of a colored map. And so you may say, oh la 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 la, I'm using randomness. Is this legal?
Well, it doesn't depend on the current map, and then the proof long time ago were conditioned on the algorithm.
Yes.
So it's fine.
So actually, you can write this algorithm depending on the map itself, just on the map, not on the colors. But let's say that the colors are given by some zeta, that's not a zeta, that's a xi. That's a random variable that you sampled before, like an infinite sample of head and tails with this Bernoulli law, so that you can decide the color. Okay, so first of all, you sample, I don't know, using a uniform random variable on 0, 1 or whatever, as you wish, you first sample that. this psi, this additional randomness, to tell you how you color the faces. And then you can write this algorithm as a deterministic function of your map, and this is used to color the faces of the map according to this additional randomness. But this, when you look at this algorithm now, you say, that's a deterministic algorithm conditionally on this. But since this was independent of the map, you first sample your color, and then you sample your map, and using your sampling of the color, you know how to color the faces of the map. Then you see that this is still valid, because this randomness is indeed independent of the randomness of the map. Okay? So if you did not notice the smell, there was no smell. Okay. So what I claim is actually that this guy, proposition, Bn evolves as a random walk started from 1, killed or stopped on the negative half line, so -3, -2, -1, 0, with IID increments of law. And let me put the law here. What is the law? So let's see what I'm doing to my black boundary during such a peeling step. So each time I will swallow this leftmost black edge. It will disappear anyway, because either I'm discovering a face and this edge is not part of the new boundary, or I will swallow it, and so here or there, and in those two cases, it is not part of the boundary anymore. So there is always a -1 coming from the killing of this edge of law -1. Then what is positive for the boundary length, for the black boundary length? The only event which makes this black boundary increase is this type of event, when you discover a new face, and this face turns out to be black. So what is the increase of the black boundary here? That's the exposed number of exposed edges, 5 in this case, times some epsilon guy, and this epsilon is just to tell you it's 1 if the face is black and 0 if the face is white. Okay? So plus little epsilon e exposed. So what is the variation of the black boundary in this case? It's just -1. I just killed that edge, and the rest is not affected. And so actually, this is just because I have not swallowed any edges on the right of my peeling point. So this is just minus g of r, which is the number of edges that I swallow on the right, like here. That's the number of edges I've swallowed on the right. So what is the number of edges I've swallowed on the right? Here, that's this part. This part is the number of edges that I've been swallowing on my right, and indeed, I'm subtracting all these edges from the black boundary. Okay? Yep.
What do you mean by law -1? So you look at these as random variable?
So
It's just a usual sum of
IID increments. The increments have this law, and I have to tell you, of course, what is this epsilon? Yes?
What do you mean by this law?
Okay, remember that law? That law, I do one peeling step, and when I do one peeling step, I have 3 random variables, which are correlated. Actually, this can only be, if this one is non-zero, then this one is 0, and this one is 0. It's only non-zero at one place. Okay, that's my triple of random variables. So here, those two guys, they are on the same probability space from this random variable, you see? And this epsilon, I have to tell you, is independent of this, of G, L, E, G, R, and 1 with probability P, and 0 with probability 1 minus P. It's just this Bernoulli P1 minus P. All right? Okay? Is that clear? From the peeling steps, that you have this? Okay. So now the proof of the theorem is very easy. So you have a random walk with those increments, and you want to know whether or not, according to the proposition I erased, you want to know whether or not Bn has a positive chance to stay positive forever. So question, can Bn stay strictly positive forever? So you have a random walk with IID increments. It's easy to decide whether this walk can stay positive forever or not. That's if and if the random walk with increments like this, -1 plus E exposed edges minus G of R, with IID increments of that law, does not drift to plus infinity. Because either this walk drifts to plus infinity, and so it can stay positive forever. Otherwise, it either drifts to minus infinity or it oscillates. And in both cases, you will see negative values. And so the walk will indeed reach negative values. All right? Does drift. Yes, thank you. Does drift. OK, so let's see a first case. First case. Let's assume that the expectation of the number of edges I'm solving on the right is finite. Then I claim that automatically this implies that the expectation of the number of exposed edges is finite as well. Why? Well, because otherwise, so what is this mu? You remember, I hope you remember the new walk. The new walk is the increment that drives the pinning process, the perimeter process in any pinning exploration. So a new increment, what is a new increment? A new increment, it's E, that's the variation in the perimeter length, so E minus GR minus GL minus 1. A step distribution nu is the law of this guy. So if I tell you that this guy has finite expectation, then this guy has a finite expectation, this guy as well. So assume that if, by contradiction, if E had an infinite expectation, what would you tell about this? This would have an infinite expectation as well. So this would imply that the expectation of nu would be infinite. And so the new random walk would drift to plus infinity. But we know this is never the case. We proved that in the former lectures. We proved that there are two cases. Either nu oscillates in the critical case, or nu drifts to minus infinity. It cannot drift to plus infinity because, for those who remember, because the renewal function h upper row is unbounded. Okay? So this implies that, for those who have not understood, this is just technical. I tell you that if the mean number of edges I'm swallowing on the right is finite, then automatically this is finite. Okay? So in this first case, when everything has finite expectation, deciding whether a random walk can drift to plus infinity is just deciding whether the mean drift is positive or not. And so, can Bn stay positive? This question is equivalent to deciding whether the mean drift, which is 1 plus P times the expectation of E minus the expectation of GR is positive. Okay? And so we will introduce a notation for this. This is little e. Well, not the same as this one. and this is little g. And what this is equivalent to is p larger than 1 plus g over e. Okay? Okay? But there is also the other case. The other case is when G has actually no moment. Okay? So second case, the expectation of G R is infinite. Then I claim that something terrible happens, that you cannot have percolation for trivial reasons. So if you have this, then the map M infinity under this law looks like this. You have the root edge somewhere, and the map looks like it's a map of the plane, but it has cut edges like this. And it goes on forever. That's a map of the half plane, right? Because the face on the right of this root edge is indeed infinite, but I claim that those guys, which I call cut edges, what are they? They are edges separating the root edge from infinity. Okay? And I claim that as soon as the expectation of the gulp is infinite, then you have infinitely many cut edges. And if you have infinitely many cut edges like this, you cannot have percolation deterministically. Even if you color everything black, so green, even if you color everything green, that's P is equal to 1 in percolation. P is equal to 1, but still the cluster of the root edge is finite because it's isolated by this cut edge. Okay? So let's see how to prove this. Let's see how to prove this. So that's a lemma. Second case, I'm claiming that this expectation is infinite, then I have infinitely many edges. Okay, so let's prove it. Proof. We will explore the map to know where are those cut edges. So how would you do that? So you start with your map, like this. And you want to know where are the cut edges. So let's see, let's test your intuition. Which edge do I want to peel first? I want to decide whether the origin of the root edge, rho here, whether it is disconnected from infinity by an edge. Which one do I want to peel? Yes, I want to peel this one. Because either this one, if this one is identified with an edge here, I'm not creating any cut edge. If I discover a new face here, I'm not creating any cut edge. But if this one is identified with an edge there, then I'm creating a cut edge, right? Then I'm creating something like this. And this is a cut edge for the origin. If now I am in a situation like that, so let's imagine, as Rémi was saying, that up, I peel and I see a first cut edge, like this. This is my root edge. Which one do I want to peel next? Same thing. I want to peel this one. So now let's see what happens. Now I tell you I discover a face, like that. Which one do I want to peel to see if I have a cut edge? Do I want to peel an edge here? Not quite, because even if this one is identified with an edge here, that would not produce a cut edge for the... So I really need to peel edges which are part of the initial boundary of my map. So the next one I want to peel is this one. Okay? You agree? So if I do so I'm not writing the details, but you've got an algorithm, let's call it a cut. You've got an algorithm that tells you which edge to peel, for which you know when you're discovering a new cut edge, it's when you're identifying this edge with one on the right-hand side, and so that the gluing of those two edges disconnect the origin from infinity. The only thing I need about this algorithm is what happens each time I'm discovering a new cut edge. So, okay, let's imagine the situation after this step. And let's imagine that this guy is identified with one edge on the right. What do I see? I see something like this. And my root edge is somewhere here. What do I claim? I claim that now the next cut edges between my root, my origin vertex, and infinity, they are in this part. And everything is now as if I were starting with a fresh, totally fresh random map and trying to decide which are the cut edges between this point and the rest of the map. Okay? So the only thing I'm claiming from that is that the number of cut edge and cut has a geometric distribution. Yep.
I was just wondering, in the first case, so just after the word proof, if when you peel the red edge, you find that it, you find that it's the same as the root edge. In this case, do you consider that you have a cut or not?
Yes. Yes. The root edge is like that. The cut edge, a cut edge is an edge separating the origin of the root edge from infinity.
Okay, so then the root edge will be itself a cut edge.
Yes. Okay? So with this algorithm, it's clear on that picture. What I'm telling you is that I can discover this part of the map in a Markovian fashion so that conditionally that I have explored this part, the rest here has the same law as an initial map. Okay, so I used that trick already for geometric random variable, knowing whether the random variable is infinite or not is equivalent to knowing whether it has infinite expectation or not. So n cut is infinite if and only if the expectation of n cut is infinite. But this is easy to compute, because if you start with the initial boundary, that's the root edge here, I can compute for you the number of cut edge. Why? Because for any guy here, I'm computing what is the probability that this guy is glued with this guy, and that they form, after the gluing, a cut edge between rho and infinity. So for any I, let me call it minus I, and this is a j, for I and j bigger than 0 or bigger than 1, I can compute what is the probability of this. That's exactly the probability that in my map, this edge is glued with this one on the boundary and they form a cut edge like that. Or if you prefer, that if I do the contour here, this is the minus ith edge, and if I do the contour here, this is the jth edge. Okay? But this I know. This is exactly the probability that if I were to peel this one, this would be identified with this one. So what is the probability of such an event? It's an event which is g infinity, and what is here? Roughly speaking, it's something like that. Something like, I'm not entirely sure of this. This depends on my notation, but this boundary length is roughly I plus j divided by 2. Let's not divide by 2. Let's assume we're not bipartite anymore. Okay? But now if you sum over all ij of this new I plus j. What is this? This is sum for all I of the tail of nu, and this is the expectation of nu. Well, not the expectation of nu. This is the expectation of the negative part of nu. Yes, because here I need a minus. Sorry, guys. Everything was okay. It's the tail, and that's more or less the expectation of this guy. Okay. So everything to say that if this guy is infinite, I have no percolation for totally trivial reasons, and otherwise I know by this argument for which p I have a positive chance that my cluster is positive, is infinite. So yes? I have not yet proved this. So let's see what I have proved. I have proved the following. We have proved that under this measure, if I sample the map, if I sample my percolation, and if I ask my cluster of the root edge is infinite, okay, then this is 0 if p is less than or equal to 1 plus g over e, and this is strictly positive if p is strictly bigger than 1 plus g over p over e. This is what I proved. Okay? And this guy is actually equal to 1 if g is infinite. Okay? It's not quite a quench statement. This is what we would call an annealed statement, because I'm telling you what is the probability under averaging both on the map and the percolation that my cluster is infinite. And I tell you this is 0 if blah, 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 and this is strictly positive if blah, blah, blah. This is not what is here. What is written here is a quench statement. It's something almost sure for this. Okay? So what do I want to prove now? I want to prove that I can bootstrap from this annealed statement to a quenched statement. But this is standard, very standard, using ergodicity of the map, which I have not proved, but let me tell you a more down-to-earth proof. So let's assume that p is less than, and we will call this guy PC. So let's assume that p is less than or equal to PC. What do we want to prove? We want to prove that in my map, there are no infinite clusters. So what do? We start with the map. We have some starting face here, which is black by definition. And you want to know whether there is an infinite cluster somewhere in that map. So what do? Well, you start by exploring this cluster. Okay, so you do the algorithm and you explore this cluster. And you know that you will finish at some point. Why? Because the probability that this cluster is infinite is actually 0. So you will finish. Then what do? You just pick another edge on the boundary that is remaining. Pick this edge, for example, and start exploring the cluster of this guy. You start exploring the cluster of this guy, and you know, by the same argument and the spatial Markov property, that you will finish at some point. So now you say, OK, let me explore a new one, and I will explore the cluster, and this cluster is finite. And now you say, oh, if I keep on going like that, I may not discover the full map. but let me now play like this. Let me now take an edge here so that I'm exploring locally the map. And I will explore this part, and then probably I will take an edge here, I will explore this part, and then this part, and then this part, then this part. And I'm doing a bit like an algorithm A-metric that we use to explore the full map. And I know for sure that all these pieces, all these clusters, they are finite. And so I iterate and I explore the full map without seeing any infinite cluster. Okay? So that proves this part. Let's see this one. Well, this one is pretty much the same. So what do? You start with your root edge and you explore the cluster. By this proposition, there is a positive probability that actually the exploration never stops. Okay, so you start your exploration, and bad luck, my cluster is finite. It happens. I mean, it happens. You just have a positive probability. What do? Just pick another edge here and start exploring this new cluster. By the spatial Markov property, what is remaining here is independent of this part. And so when you start exploring this new cluster, there is still a positive probability that you will never stop. And if you never stop, you have found, bless you, you have found an infinite cluster. Okay? And since you may, each time you fail, you may make a new sample, there is a chance 1 that at some point you will manage to find an infinite cluster. Okay? Have I proved the entire theorem? Yes. So I proved this, there exists an infinite cluster, and I have not proved that this cluster is unique. So let's see why. Okay? Woo. So let's see why. For this, if we want to prevent the existence of two infinite clusters, we will focus on this. Let's assume that I start with this boundary condition. I have some black part here, some white part, and then some new black part here. And you will be, I hope you will give me that for free, that if I prove to you, that if I tell you that there might be two or more infinite clusters, then there is a positive probability that this is actually in some infinite black cluster, that this is in some infinite black cluster, and that they are disjoint. Okay? So what we want to prove is that you cannot start from this boundary condition, this one being in an infinite cluster, this one being in an infinite cluster, different from this one. Okay? Okay. So how will we manage to do that? Same peeling algorithm. We will be here and peeling at that edge. Okay? If we do so for example, we discover a face like that, I don't know, and this is green. That's good for me. Why? Because I'm starting increasing this boundary length. And now we will peel on that one. And probably, I don't know, maybe this one is identified with this one. But if this one, then I will peel on that one, say. And if this one is identified with this, then I'm doomed. I'm doomed because these will not be the same cluster. These will be the same clusters. Okay? So if I want this exploration to succeed, meaning that this part is infinite and different from this one, I need that during this exploration, I need that this boundary goes to infinity, does not touch 0, and this white boundary also does not shrink to 0, that this white boundary remains. Okay? You agree? So let's put W here and B here for those process. So Wn is the length of this white boundary, Bn is the length of this black boundary. What is the evolution of Wn plus Bn? Okay, so you may come down to earth and say, okay, if the face is black, then Bn increase and blah, blah, blah. But actually, I think this is just a new increment. Plainly, because the new increment is the increment in the boundary length during one peeling step. And if both the white and the black remain positive, that means that all the increments of this process, they will make the perimeter vary among those white and black. So it's exactly a new increment. Or if you wish, okay, no, it's a new increment. As long as W is positive and B is positive as well. And now we're done. We're done because we know that a new random walk either oscillates or drifts to minus infinity. So we are sure that if we do a new random walk, we will reach negative value. So this guy cannot stay positive, W plus B. It cannot stay positive. So W plus B cannot stay positive because a new random walk does not drift to plus infinity. That means that either black or white becomes negative. And we're done. Because if white becomes negative, that means that we had a peeling step identifying those two black boundaries. And if black becomes negative, that means that we had a peeling step identifying this with this, and so that this region is a finite region, finite black region. So, yes?
If we identify with the edge on the left of the left black boundary.
If you would have peeled here, that's your question?
More on the left.
You want to peel here? You want to peel here?
Yeah.
Why?
Then we do not connect these two black faces, clusters.
Yeah, but you need to explore those to know whether they are in an infinite cluster or not. So, yeah.
So if the left cluster is infinite, then we cannot identify it.
Yeah.
So you're conditioning on the fact that...
Yeah, actually I'm not, but I'm saying that as long as W plus B is, W and B are positive, this is given by a new increment. And since I know this Markov chain, will enter values where either this one or this one is negative. If I swallow the black part on the left, I swallow Wn as well. Wn is just this. So if I'm doing a peeling step like that, then I'm even more happy because I know that Wn disappears, and I know that if Wn disappears, I'm claiming that those two guys cannot be both infinite cluster, both different infinite clusters. You see what I mean? I mean that, okay, what I should have written is that if this guy is an infinite cluster, this guy is an infinite cluster, and they are different, that implies that the process Wn and the process Bn during this exploration, they both stay strictly positive. Actually, I'm lying a little bit here. Does anybody see why? If somebody sees why, then I pay a beer. You got a beer. Have you read the lecture notes? No. Sure? Okay, you get a beer tonight. Yes, actually Wn can become 0 and they may still be different cluster. So actually, I want this guy to become -1, -2, strictly negative. But that's the same. All right? Okay, so this has 0 probability of happening, and so with the same argument on the little board, we see that there is never coexistence of infinite cluster in those maps. Okay. So now let me do the same thing. Something that I have not told you about. So this PC, so what is this PC? This is 1 plus G over E. But actually, we can simplify the notation. I claim that if we're in this case, for which the PC, so this is, or PC is 1 if G is infinite. I claim that we can simplify the notation a bit more, because remember, so what we just said is that if G is infinite, if this mean gulp is finite, then E and G are finite. And so what is the expectation of nu? So we said that nu, remember, nu is the expected variation of the perimeter process during a building step. So this is E minus 1 minus GR minus GL. By the very definition of this guy, because this is the number of exposed edges, so the edge you add to the perimeter. This is the edge you peeled, and those are the edges you swallow on the right, and those are the edges you swallow on the left. So this is equal to E minus 1 minus 2G by symmetry. And I actually claim that this is 0. Why? Yes?
You told us last time, right, that because it oscillates, it must have mean zero.
Why should it oscillate? Yes, you're right. I claim that in this case, this should be equal to 0. Okay, that's a lot of stuff, but we did that. We said the new random walk either drift to minus infinity, and that's the subcritical case. That was the subcritical case. Or the critical case, this random walk oscillates. Can we be in the subcritical case here? So what was the subcritical case? Subcritical case is this for the FQ. Remember? And we said that yesterday, we said that if we are in the subcritical case, then the negative tail of nu, this is decaying like constant k to the minus 3/2 for k going to plus infinity in the subcritical case. We did that yesterday. So can we have a finite expectation for nu with this tail? Impossible. So this implies nu is critical. So nu, random walk, oscillates. And now, since you have a one-dimensional random walk, you know it oscillates. Since it has a first moment, you know it must be centered. And so, actually, this is equal to 0. So we can replace here E by 2G plus 1. Okay? Okay.
Nico?
Yes?
Before, when you drew the picture with the cut edges, couldn't you have had a tree instead of just a line?
It will look like a tree. It will look like a tree, but if you... Okay, let me do the picture. It will look like this. But what are those cut edges? Those cut edges are those ones. Infinity and...
So the scaling limit is indeed this here.
Open question number 10 or whatever. That's probably an easy open question. Nice research paper. If Q is subcritical, show that the scaling limit of this divided probably renormalized. So you renormalize by lambda the distances, and this should converge in the Gromov-Hausdorff sense towards an infinite CRT. For those who know. For those who don't know, don't look at this open question. All right? But yes. Okay, so now I want to do something a bit more exotic. It's the same thing, but not with P, but with H. Oh, what was that? The H probability measure was also a probability measure on half-planar maps. But remember now the peeling was probability to discover an event like that, CK. It was nu of k minus 1 with a tilde, and a probability to discover this G infinite k event. This was nu tilde of minus k minus 1 for k less than minus 1, and here for k bigger than 1. Okay? Exactly the same as for P, except that I had a tilde. Okay? You remember that was the definition. You could take that as a definition of those maps. These are those maps for which the peeling process has those probability transition. And remember what was those nu tilde? Nu tilde associated to nu via the following formula. You remember we had this Kramer assumption that there exists some omega bigger than 1, so that this was equal to 1, k in z. This was equal to 1, Kramer assumption. So this nu tilde of k was just the exponential tilting of the nu. And this guy was subcritical, remember? But then if you do this transform, so subcritical means that a new random walk drifts to minus infinity. But you remember after this tilting, we could say that a new tilde random walk actually drifts to plus infinity. Remember that? Okay, so now let's play the same game. We play the same game as here. We fix an admissible weight sequence. We suppose it's subcritical and Kramer. And then we ask what happens for the percolation. Okay? So that's not the, okay. Up, there will be a different phenomenon appearing. So let's see what happens for the percolation. So you start exactly as before. You start exactly as before by saying, okay, if I apply this peeling algorithm, I have my black boundary, and I want to peel the edge which is leftmost on the black boundary and see what happens. Okay? And so same thing, the process Bn tilde will evolve a killed random walk with increments. What are those increments now? Well, I claim it's the same, minus 1 plus E tilde with the E epsilon here minus G tilde of R. And what are those random variables? G tilde, L, E tilde, and G tilde of R. That's the same number of swallowed edges on the right, number of exposed edges during a peeling step, and number of swallowed edges on the right. So far, so good, right? I just put in tilde. And so what do we get? We get that Bn. So let's suppose the same thing. So Bn can stay positive forever if only if, okay, if only if this walk has a mean drift which is positive, which is -1 plus p times e tilde minus g tilde is strictly positive with obvious notations. So what are those obvious notations? What is e tilde? Just the expectation of this guy. And g tilde is the expectation of this guy, exactly as before. And so you want to say, oh, okay, so I want to define pc tilde when this guy is equal to 0. So 1 plus g tilde over e tilde. Okay? Then you may wonder, you may say, but he made a dichotomy between the case where g tilde has finite expectation or not. For this guy, nu tilde, remember, always has an exponential tail on the left because we were tilting a probability distribution by an exponential. So automatically, nu tilde, has an exponential tail on the left. So that means that this guy is automatically finite. Okay? So you want to say same thing. So if p is less than pc tilde, which is 1 plus g tilde over e tilde, then no infinite cluster. And if p is strictly bigger than pc tilde, then exists infinite cluster. Same proof as before, exactly the same. To say, let's see if there is a unique infinite cluster here. Let's put a question mark instead of an exclamation mark. And so you copy past the same proof as we did. You start with 2 black clusters, one here, one here. And you want to know whether those 2 black clusters can be infinite and disjoint. Okay? So what did I do? I said, we will do the peeling process with this percolation algorithm here. And we will see what is the evolution of Wn and Bn. Okay? This is what we did. And I said, but the evolution of Wn plus Bn, as long as they are both positive, the evolution of this is just a new random walk. So it has to hit negative values. Can I do the same here? This is a new tilde random walk. Aha! But my new tilde random walk drifts to plus infinity. So I cannot apply the same argument. So let's see. Let's see more precisely. And let's look at the evolution of this Wn. Okay? So the evolution of this Wn is again a random walk, killed when it becomes strictly negative. And what are the increments? So let's see. So if you discover a face like that, which is white, what is the effect on Wn? If you discover a white face here, nothing. It does no harm to Wn, right? If you discover a black face, what is the effect on Wn? Nothing. It does no harm to Wn. If this edge is identified with an edge on the right, what is the effect on Wn? Nothing. So the only effect you have on Wn is, sorry. Yeah, when it was white, but you should stand up and say, no. Sorry, when it was white, of course, it has an effect on Wn. So with probability 1 minus epsilon. So this is 1 minus epsilon. If the face is white, you add this E tilde. Sorry, you add this part to the Wn because this becomes the white region. Thanks, Pascal. Thanks, Jean-François. But you should be more reactive. And the last case is when this is identified with an header on the left. And here, what do you remove from Wn? By definition, you remove the edges you swallow on your left. So let's see what is the mean of this. The mean of this Curien random walk. So it's 1 minus P E tilde minus G tilde. Aha, so you want to say there will be some other parameter which I will denote by PU tilde, which is defined by equaling this to be 0. So what is it? 1 minus G over E tilde. No. Okay. Let's do that step by step. It's P E tilde is equal to E tilde minus G tilde. And so PU tilde is equal to PU tilde E tilde minus G tilde over E tilde. Okay? So now you want to say, if P is strictly less than PU tilde, then what cannot appear? So in this region, this Wn has a negative drift, and so this will shrink to 0, so I cannot have two infinite clusters. So there exists a unique infinite cluster. And if I did it just before. Yes? And if P is strictly larger than PU tilde, then there will exist infinitely many infinite clusters. Okay, let's do a sanity check. The sanity check is to check that PU is larger than PC. So what is PC again? PC tilde is 1 plus G tilde over E tilde, and PU tilde is E tilde minus G tilde over E tilde, right? Yes?
Something disturbing me, if you take P equal to 1, the infinite cluster will be infinite. That's not what you have written.
Okay. Yes. You cannot take P is equal to 1. Yes. Yeah.
Okay.
So in the hyperbolic case, yes, P is non-trivial.
So first you see one infinite cluster.
So let me first do the sanity check. I need to rush, and then I come back to you. So the sanity check I want to do is this. I want to check that PC tilde is strictly less than PU tilde, which is equivalent to 1 plus 2 G tilde should be less than E tilde. Is that correct? But it is the case. Why? Because under nu tilde, what is the expected change of my perimeter? It's always minus 1 because of the edge I peel, plus E tilde because of the new edge I'm exposing, minus twice G tilde, the edges I'm swallowing. And I know that this is strictly positive because nu tilde drifts to plus infinity. And so I know that E tilde is strictly bigger than 1 plus 2 G tilde. And so this is correct. And so the picture is the following. You have 0, 1. You've got a first parameter, PC tilde, a second parameter, PU tilde. And in terms of infinite clusters, you know that here you've got no infinite cluster up to here. Here you've got one infinite cluster up to here. And here you've got infinitely many clusters up to here, up and here.
I'm also puzzled like Rémi because I mean 1 minus P is if you flip black and white then we exchange the roles of black and white, then if
It's not
P is
self-dual.
large,
It's not self-dual. If you exchange black and white, you don't get phase percolation on. It's the dual of phase percolation is phase percolation where two faces, when they share a vertex, they are actually part of the same cluster. It's not self-dual, but easy exercise for you guys. You can do that for the yes.
Are you really sure that you shouldn't flip infinitely many clusters below PU and one infinite cluster above PU?
Let's see. Okay, probably you're right because there is a minus p. Yes, thanks. Yes, infinitely. Let's do it. Yes. Yes. Yes, and then there is continuity. One up to here. Sorry. Yes. Yes. Yeah, it's always like that. Yeah. You're right. But I was the nose in my computation. All right. So, yeah. Okay. So I need to stop. But so I hope it was not too quick. But the message is again, we can study percolation very easily because proving such kind of theorems for deterministic lattice would take 30 hours. I mean, the PU phase, the PC phase, identifying the PC, showing there is no percolation at PC, showing there is there is infinitely many clusters at PU. For deterministic lattice, these are very hard questions, very, very hard. And here there is a clear picture in a blink of an eye. Okay, I was quick, I know, but there are many open questions in the lecture notes. And for example, nothing of this in this generality is in the literature. So extending this to maps, hyperbolic maps of the plane, for example, or getting everything working, yes, map of the plane, either hyperbolic or not, that's not in the literature, and there is some interesting work to do. So if you want to join, this is a good entry door. Second thing I want to tell you, but I just forgot. Ah, yes. There is also a nice open question I want to mention for those interested in geometry. So, open question, and I finish with that. Open question. So, go at PC tilde, critical threshold for existence of infinite cluster. Go there and study one cluster, the cluster of the root. So you know that this cluster is finite with this picture because at PC there is no infinite cluster. But study the cluster of the root conditionally on the size of this cluster being large. So you want to study large critical cluster in this hyperbolic version. Then open question. I think that C properly renormalized by, if you look at this as a metric space and you normalize distance by square root n, this should converge in the Gromov-Hausdorff sense towards a version of the CRT. And if you want to approach this problem, you let first Thomas win the ping pong tournament, and then you go to David. Where is David? Here. Because he's doing similar things as well for critical cluster in hyperbolic setup. All right? And so the day after tomorrow, right, it will be a final lecture. We will be studying the metric property of those maps, both in the plane and the hyperbolic plane, using the peeling process. And we'll see that they have a very different volume growth, R to the 4 in the critical case on the plane, and exponential with corrections in the hyperbolic case. That's all for today. Thanks.